Okay, so we'll go through one more example. Now, if you look at the time complexity and space complexity here, it's just like for a graph of n vertices, you have to go through n iterations, and in each iteration, what we are really trying to do is trying to fill up each of these cells, right? So, of course, the particular row and column will remain the same. So, we are going to fill n square cells in a matrix of dimension n by n. So we are going to spend n square time for each iteration, and we have n iterations. So n square times n is n cube. Okay, so we'll have a nested for loop. So we'll fix your k from 1 to n, and then you try all combinations of I and j by going through k. Okay, so it's very simple to implement. Then the space complexity is going to be n square because you have to maintain these two matrices. So each matrix is n square, so it's n square plus n square, which is 2n square, it's still n square, theta of n square. So it's a dynamic programming algorithm, so you have to allocate some space to store the result values, the intermediate result values. Now that also means that in an exam I can ask you, okay, so after you identify or run through the algorithm, or even instead of asking you to run all the n iterations, I could give you a graph of 4 vertices like this, but I can ask you to find the shortest path distance by considering only vertices 1, 2 and 3 as the possible intermediate vertices. That means you'll do only up to iteration 3, because when I say only vertices 1, 2 and 3 or the possible intermediate vertices, then you do up to only iteration 3. It could be also like what I do for the other problems. So in like the other dynamic programming problems you have seen, you go through all the 4 iterations and you find the shortest path distance by considering all possible combinations of the vertices. And then you can also use the results of the earlier iterations and say, okay, this is the shortest path distance I can have only up to by considering only 1, 2 and 3 as intermediate vertices, and this is the shortest path distance I can have by considering only vertices 1 and 2 as the possible intermediate vertices. You see here, as you limit the number of vertices that you can consider as intermediate vertices, some of the distance estimate will be infinity, because that's the best you can do by considering only vertices 1 and 2 as intermediate vertices. From V2 to V4, there's no path from V2 to V4 by considering only vertices 1 and 2 as intermediate vertices. So that's why the distance is infinity. Okay, so you have to basically understand the fundamental thing behind this algorithm. Okay. All right. So let us go through one more example quickly. We may not do all the iterations, just one, just to explain the idea. All right. So. Okay, so here I have given you a graph. Let me make sure I have started the video. Yes. All right. So now, if the graph is very congested like this, I may not give you the edge weights right away along with the edges. So I could give you the initial distance matrix right away, which is also the edge weight matrix. So I could give you only the distance matrix, and using that you should be able to come up with the predecessor matrix. Why? Because if there's an edge from one vertex to another vertex, then you're going to have some edge weight, and that means say for example from V1 to V2 there's an edge, so the edge weight is 3. That's also the initial distance estimate from V1 to V2. And the predecessor from V1 to V2 is going to be V1 itself to begin with. Okay. Now, if there is no edge, say there's no edge from V2 to V1, so then I would have given as infinity as the distance, as the edge weight. So from V2 to V1, if it's infinity, that means there's no edge to begin with. So V2 to V1, the predecessor is not applicable. So that also means I need not even give you the graph. So that may be the case because it may be again very congested for me to draw for each of you a graph. So for each of you, for exam, I could just give you the distance matrix. So this alone is sufficient for you to work with, because Using this, you can come up with the predecessor matrix and move on. The graph is just for our reference, whether to see visually whether it's an edge or not. Using the initial distance estimates, you should be able to tell whether there's an edge from one vertex to another vertex. Like for example here, it is infinity from V1 to V4, so there's no edge from V1 to V4. It is -4 as the edge weight from V1 to V5, that's okay, some edges could have negative edge weights. And this is 0 again in the diagonal to begin with, because there's no self loop from V1 to V1 or V2 to V2. But since some of the edge weights are negative, as we go through the iterations, we have to kind of also check whether can we go from a vertex to itself through a path of weight less than 0. It is possible, because by going to some negative weight edges, we could reduce the distance from a vertex to itself to a value less than 0. So if your initial distance matrix has negative edge weights, even one negative edge weight, you would have to carefully check that diagonal entries too as we go through the iterations. Okay, so again, for exam, I'll probably assign each of you just the distance matrix, and you can work on based on that. All right, so let us now go through the first iteration. So this is what, as I said, I'll give you the weight matrix. So if I give you the weight matrix, you should be able to, it's the same thing, the initial distance matrix, and write the predecessor matrix too. Alright, so in the first iteration, you highlight the column and row corresponding to vertex 1. So this is vertex 1, column and row. So you're going to see if you can reduce any of the entries in the other cells. So it is 0 now from V2 to V2. So you're going to again highlight the row and column. So here it's going to be 3 horizontal and vertical, it's infinity horizontal, vertical is 3. So 3 plus infinity less than 0. No, so stay with 0. So, and then again, since we're going to go through V1, write down the predecessor entries we have for row 1 and column 1. And then also we are going to use these entries for row 1 for the predecessor. Now since here it is 0, same as our previous distance, we are not changing the predecessor, so write down not applicable, whatever is the predecessor entry here from V2 to V2 is same as the entry here. Okay, now the distance, now you should also be able to quickly do this, because by now you should have figured out if one of the two values you're adding up is infinity, like in this case, to fill up any entry in this row, you're going to add this infinity with any of these entries here. So it's going to be infinity plus 3, infinity plus 8, infinity plus infinity, infinity plus -4. So for this row, the entry is infinity. One of the two values will add up as infinity plus something. So that's going to be still infinity, right? Infinity plus anything is still infinity. So that's not going to reduce the values further from what we have. So that means I can right away say copy the values 0, infinity, 1, 7 as the entries here, because I'm not going to be able to reduce them further, because one of the two entries you're going to add up is infinity. So that means we can write down also the predecessor entries as it is, not applicable, not applicable, then V2 and V2 for this row V2. Okay, so that's what we can do as an kind of to do things quickly, for example. Now similarly in this row here, I'm going to add infinity plus 3 to decide about this cell, and for this cell I'm going to add infinity plus 8, and then infinity plus infinity, then infinity plus -4. So it is one of the two entries is infinity, so the result is also going to be infinity. So I'm not going to be able to reduce from what we currently have. So I can also write 4, 0, infinity, infinity here. And the same predecessor entries, V3 not applicable, not applicable, not applicable here. So when one of the entries is not infinity, actually when both of the entries, because it's easy to look at the row for visualization, right? So when a row entry, what do you call this as a column? So when your column entry is not infinity, so like in this case, it is not infinity, it is 2. Then it's better to to be careful. You can add this 2 with each entry in this row and check whether it can reduce. So it's going to be 2 plus 3, 5, less than infinity. So we can make this phi, and then whatever is the highlighted in the v1 2, this is v2. So in this row for v1, the column is v2 because we're trying to go from v4 to v2, going through v1. So from v1 to v2, the predecessor is v1. So write down v1 here from v4 to v2. Okay. Now similarly here you see the highlighted row where horizontal is 2, then vertical it is 8. So 2 plus 8 is 10, not less than negative 5. So write down negative 5 and whatever is the predecessor v4 here. So only if you're going to change the predecessor, look for that row for v1. But if not going to change the predecessor, not going to change the distance, the predecessor is also not going to change. So write down v4 as it is from v4 to v3. Now this is 2 horizontal, vertical, infinity. Infinity is a sum not less than 0. So write down 0 and whatever is the predecessor not applicable here. Now for this cell it is horizontal 2 and then vertical negative 4. So 2 plus negative 4 is negative 2, not less than, sorry, it is less than infinity. So we can write negative 2 here, and since we changed the distance or reduced the distance, look at the row for v1 and looking at this cell, so to v5. So to v5, from v1 to v5, the predecessor is v1. So write down v1 here. Okay. Now for this cell, it's easy to visualize that, see that the row entry is infinity here. So we are going to add everything with infinity. That's not going to change any of these. So we can write down infinity, infinity, 6 and 0 as the values and the corresponding predecessor entries. Okay. So I hope this is clear how to go through this example. So in the second iteration, we are going to highlight the row 2 and column 2 and go through the same process. So for example here, to fill up any of these 4 cells, right? So to fill up any of these 4 cells, I'm going to do what? So let us say if I want to fill up this cell, the highlighted horizontal line will reach, so vertical line will reach here at infinity, horizontal will be 3. So it's going to be infinity plus 3, infinity, not going to be less than what we have here. So that means for this cell it's going to be infinity plus 4, for this cell it's going to be infinity plus 5, for this cell it's going to be infinity plus infinity. So once you carefully identify whether the one of the two values you're going to add up as is infinity, then like in this case this column is going to be not going to change because you're going to add infinity plus something to update the entries in this column, and that's not going to be less than the entries in this column already. So we are going to write whatever is there. So 0, infinity, 2 and infinity as the values, and the corresponding predecessor entries, not applicable, not applicable, v4 and not applicable. So that's how you kind of could decide. Similarly, this column you are not going to be able to reduce anything from what we have, because for this cell it's going to be infinity plus 3, not going to be less than what we have, infinity plus 4, again infinity plus 5, then infinity plus infinity. So we can write whatever we have already. But for this column we are going to, we have to check because we have 1 here, and that means we are going to add with 1 plus something, 1 plus something and so on. So it's better to check. Similarly for this column we are going to add 7 plus something, then 7 plus something, 7 plus something and so on. So it's better to check. So that's how you could decide to fill up the entries in an exam to do it kind of more quickly. So you can go through the iterations. So this is a graph of 5 vertices, so you will have to go through 5 iterations. At the end of the 5 iterations, you are going to have this as the distance matrix and this is the predecessor matrix. So that means this distance will be the shortest path weights of the paths from one vertex to any other vertex. So this is all paths shortest path. So let us try to identify a couple of paths. So V3 to V1. So V3 to V1, it says V4 is the predecessor. That means we have to go from V3 up to V4 and then take an edge to V1. So V3 to V4, it says V2 is the predecessor. So we have to go from V3 to V2, and then from V2 we can go to V4. So V3 to V2, the predecessor matrix says V3 itself is the predecessor. So V3 to V2, there's an edge. So this is the path from V3 to V1, and you can cross check whether the sum of the edge weights add up to the path weight. Of course, I did not give you the edge weights on the graph, but have given you the initial weight matrix, right? So you can make use of the initial weight matrix. V3 to V2, the initial the weight matrix V3 to V2 is 4, and V2 to V4 is 1, so 4 plus 1, 5 so far, and V4 to V1 is going to be 2, so 5 plus 2, 7. So 7 is the path weight from V3 to V1, and that's the path weight we have from V3 to V1. So you can always cross check whether everything is right. Okay. Similarly, from V1 to V3, the predecessor is V4. So that means we have to go from V1 to V4 and take an edge from V4 to V3. V1 to V4, it is V5. So V1 to V5, and then edge to V4. So V1 to V5, the predecessor is V1 itself. So V1 to V5 is an edge. So again, you could find out the edge weights from the weight matrix, add them up. It should come out from V2 to V3 as -3. Okay. So I think everyone is clear about it. If you have any questions, you can ask over the microphone or message me. Let me save this as a video.